Hi, everybody. Cool. So that was a really fun discussion, talking about Werewolf and cluster provisioning and going through that demo of doing that. So I think what I'd like to do, and it's going to be, I'm going to go ahead and present for a while, and then my colleague Jonathan is going to present. We're going to kind of go back and forth. But I think what I'd like to go ahead and do for the rest of the session is to talk about kind of filling that the rest of the software stack out. So now you've got the cluster provisioned with Werewolf. And so I'm going to talk about Apptainer to begin with, and kind of, that being the next step in the building block of your cluster. I think Jonathan's going to take over at that point and then start talking a little bit about MPI with Apptainer and some new developments which have made fully containerized MPI a lot easier and a lot better. And then I'm going to finish off talking a little bit about container orchestration and really talking about HPC everywhere and how we are doing that and how we're enabling that at CIQ. Okay, so my name is Dave Godlove. Just to kind of introduce myself a little bit, I kind of started off as a primary research scientist at the NIH as a neuroscientist, and then from there became interested in high performance computing. I joined the BioWolf staff at NIH and helped to administer that cluster as a staff scientist for a while. And then I've been around the Apptainer community for a long time, really since the Apptainer community first became a thing and Greg first started developing Singularity. So that's kind of my background here. I'm going to start off with a few slides, but I'm not going to do too many slides. So the previous part of the discussion, was fairly high level as far as provisioning out clusters, using Werewolf and everything. So some of this might be a little bit kind of low level, then jumping from high level to low level. But I'm just going to do a little level set here and just talk a little bit about Apptainer. And hopefully in this presentation, I'll span all the way from really low level concepts all the way to more advanced concepts by the end of this portion of the session. So you might be maybe asking yourself, what is Apptainer? And in a nutshell, Apptainer is just the Linux Foundation successor to Singularity. And so you may, I don't know, be asking yourself, what is Singularity? And so without getting too much in the weeds, I think the best way to understand Singularity is to just think about the origin story and where Singularity first came from. I'm going to cover this really fast. Many people might have heard me or other people kind of, talk about this before in the past at other meetings, but basically 7-8 years ago, Docker was really popularizing Linux containers within the development space, right, with developers. And HPC users took notice and they wanted Docker on their systems. And many people who were around in HPC at that period of time, like myself and Greg and others, looked at Docker and said, well, for one reason or another, it's not a very good fit for HPC. And so Greg, at the time at Lawrence Berkeley National Labs, decided to do something about that. He said, well, if we created a solution like a container solution specifically for HPC, what would that look like? And he, took the initiative and began the Singularity project and began to create Singularity. Kind of the most basic thing he did to enable this was to create a privilege model that just essentially, at a really high level, takes the same multi-tenant privilege concept that's already on the host system in the Linux kernel and extends that into the container. So it makes multi-tenant systems, or makes containers work then for multi-tenant HPC types of systems. And then while he was at it, and he and the rest of the community, we decided, if we're going to build this container solution from the ground up, what are we going to put in it, which is HPC centric? And so we decided to add things like, native integration with MPI, native integration with GPUs, sensible defaults that integrate the underlying file system into the container at runtime, things like this that just sort of make Apptainer work better for HPC. Since then, Apptainer has really become a basic building block of high performance computing. Pretty much any kind of conference or anything I go to anymore, like it doesn't matter if I'm in a session which actually has anything to do about containers or not. I'll pretty much always hear people talking about during the session at some point, containers are going to come up, Apptainer is going to come up, Singularity is going to come up. People are going to start talking about it because it's just such a basic thing that's on HPC systems anymore. Since it was first created, there's been a lot of innovations added to Apptainer. I want to highlight a few of those. I'm going to be talking briefly about it, but one of the things that makes Apptainer a little bit different is that it uses the Singularity image format, which is a single file format to store containers. And this gives you the ability to do things like sign and verify your containers. So using this, you could basically create a container instead of from another container. You can create one from upstream operating system mirrors, for instance, and then you can sign that container, and you can use that as a base container to track your software supply chain and to make sure that you know every single piece of software that goes into your container. And as you build, more containers from that one, and you continue to layer up, you can continue to sign and verify those containers to ensure your software supply chain. So that's something that is kind of unique to Apptainer. Another thing is the ability to encrypt your containers and to run them encrypted. So what I mean by that is since the container image is in a single file, you can, just using the tools that are provided with the Apptainer installation itself, you can encrypt those containers, and then, when you run them, they remain encrypted on disk. A little bit more recently, we've added the ability now to build containers without any privilege. And so this requires that you be on, a relatively recent like Rocky 8 or EL8 system, that or more. Basically, you need to have the user namespace enabled in the kernel. But if you do that, you're able to build your containers without any privilege, which is both convenient and also from a security perspective, a lot better than building your containers with root. And this is very recent. I'm going to be talking about this today. Very recently, we've added, I say we, this was primarily something that was just championed by Dr. Dave Dijkstra at Fermilab. The ability to install Apptainer completely unprivileged in an unprivileged and actually even relocatable way has now been added. And I'm going to do some demos today, and I'm going to show that installation of Apptainer completely unprivileged that an unprivileged user can do. And once again, this utilizes the user namespace, so you need a pretty recent kernel to do this. But if you're like an HPC admin on a cluster which has a is on Enterprise Linux 8 or above, then your users, you don't even have to install Apptainer. Your users can come and install Apptainer in their own space by themselves at this point and can build their containers without any root privilege and just do everything they need to do. Okay, so I don't want to spend too much time on slides. I'd rather spend most of my time just kind of showing you what I'm talking about here. So I'm going to be doing my demos today on this Rocky Linux, box here, and just to let everybody know too. I mean, so I'm here representing CIQ. Jonathan, my colleague, is also here representing CIQ. So CIQ obviously helps to develop and support a lot of projects and products, and Rocky Linux is one of those projects. So we help to support Rocky Linux, and that's one of the things. If you are running Rocky and you want some support for Rocky, then CIQ is the company to talk to. Okay, so let me go ahead and start a terminal. Let me make it a little bit bigger. Hopefully everybody can see that. All right, so I'm going to start off today. So I don't even have Apptainer installed on this machine, and that's by design. So I wanted to show you what an unprivileged installation looks like. So I've got here a demo directory. I'm going to run everything from within that demo directory. If you go up to, you can kind of follow along with the first part of this demo at home if you're quick on the draw and if you'd like to do so. If you want to go ahead, if you're on a Linux system too, and you want to go ahead and install an unprivileged installation of Apptainer, really what you need to do that is if you go up to GitHub and you look in the tools subdirectory of the Apptainer GitHub repo, you're going to find this install unprivileged.sh script. And this is a script which was written, once again, I'm going to call out Dr. Dave Dykstra at Fermilab. He wrote this script, and it's really, really convenient for any user to just be able to download that script and just use it to install Apptainer. I'm going to show you how that works really quick. So I'm going to make that thing, I'm going to make it executable. And I'm going to go ahead then and just run it and get the help out of it so I can figure out how to run it. So it gives me the usage here, and this distribution and arch and version are the three things I can change here. The distribution and arch are going to be pulled automatically from your host system. It's just saying, what operating system are you running and what architecture. The version is something you can change. So, and that refers to the version of Apptainer that you want to install. And then you give it an install path. So I'm going to go ahead and make a directory within my home directory where I'm going to install this. So I'm going to call that Apptainer 1.1.5. Okay, and now that I've got that, to go ahead and install this, really all I have to do is run the script. I'm going to give it the version of Apptainer that I want to install just to make sure that I installed, that version that I want. And then I just give it the directory that I just created. And that's going to go ahead and install Apptainer. Now, this is really cool. I want to draw your attention to this. Because what's actually happening here is that this script is going up to the repos, in Rocky Linux and Fedora and so on, where Apptainer and its dependencies reside, and it's getting the RPMs, and then it's extracting the RPM data, and then it's installing all of the RPM data into this relocatable directory, which is kind of cool. So it's kind of like Dr. Dave has written a little script which will allow you to do like a DNF or yum install in the directory of your choice as an unprivileged user, which, maybe I'm easily impressed, but I think that's pretty cool. All right, so now that I've got that installed there, I'm going to go ahead and I have to, of course, add the binaries to my path. So I'm going to do that. There are two places that you want to be cognizant of when you're adding this to your path here. One is just the bin directory. So this is the 1.15 subdirectory in Apptainer, and so this is the bin directory. And the other one is there's an x86-64 and there's a bin directory there, and you want to add both of those. Okay, so I'm going to go ahead and add those both to my path. And just in case I have to exit this shell and come back in, I'm going to go ahead and add those both to my .bash rc. Okay. And once I do that, I should see Apptainer on my path. And I can do things like check the version and get help. And all as an unprivileged user, I now have Apptainer installed on my system. Okay, so I'm going to do now like the most basic container demo that you can possibly do, which is to look at your operating system. And, most people I think are pretty familiar with the concept of a container at this point in time. That, one of the things that a container allows you to do is swap out your operating system with something different. But just to drive that point home, I'm going to execute the shell command within Apptainer, and I'm going to shell into a container from Docker Hub using this syntax. And it's just going to be the standard like Alpine container from Docker Hub. And it's going to go ahead and download that container for me and, create a CIF file. That's that Singularity image format file that I was talking about earlier. And now I can see that my prompt has changed. That indicates to me that I'm in a container. And if I cat etc os release, you can see that I'm in this Alpine container. Now, obviously, just swapping out your operating system with a different operating system is, sort of has limited utility. Really, what most users within HPC and with other domains want to do with containers is they want to use applications that they don't have installed locally on the system. So for instance, I don't have R. Let's say I'm a scientific user who wants to run some statistical packages or something using R. I could install R on my host system, but maybe I don't have the privileges to do so, or maybe I just, don't want to or whatever. So instead, I could do Apptainer shell Docker, and the official R image is R base. So I could do something like that. Instead of doing that, I'm going to show you another command with Apptainer. I'm going to use exec instead, and exec basically says, take this container and execute whatever command I give you in the container. So this is going to download this R base container, and it's going to pop me into this this R prompt. So now I can use R. So I'm going to go ahead and quit out of here. R asks if you want to save the workspace when you quit. Okay, and then also just to kind of round things out a little bit, containers have metadata inside them that lets you know how to run your container, what to do when you run the container instead of just executing it. So with this example, if I were to run this container, very sensibly, it says you want to run R, right? Another thing that's kind of, makes Apptainer a little bit different is when you execute a command to pull a container, what you end up getting is you actually download. So I've got several different directories here and things that I haven't shown you yet. We'll talk about those later. But you actually end up getting a file. And this is the Singularity image format, the CIF file I was talking about. And now that I have this file locally, I can do things like Apptainer exec rbase. I can just run it directly from that file. Or one of the cool things, you can see that this file is actually executable. So instead of doing Apptainer run and then rbase.cif or whatever, I can actually just run it like that. And so that's one of the cool things that you can do. And I'm going to show you a little bit later in this demo, using kind of a similar trick, how you as an HPC administrator, perhaps, or even as a user, can install programs directly on your HPC system and make them look and behave just like programs which are installed on bare metal outside of containers, to the point that your users who are using these programs don't even have to be aware of Linux containers, that Linux containers exist, what they are, anything like that. They just use the programs and everything just works. But that's going to be a little bit later. Okay, so that's very basic look and feel of how to interact with, how to run containers off of Docker Hub. I now want to talk a little bit about building containers. Bear in mind that everything I'm doing here is with an unprivileged installation of Apptainers. There's no privilege, there's no SUID bit, there's no privilege being used here. This is a completely unprivileged installation. Okay, so I'm going to build a little demo container, and I'm going to containerize a program that I like to play with called Askinema. Askinema is it's a program which has been around for a little while. Many people might have heard of it already. It basically allows you to record a terminal session and play it back like a movie. And it's got kind of a fun community around it. And so I kind of like to play around with it a little bit. But I'm going to go ahead and show you, just really basically how to build a container. So to build a container, like in the OCI world, you would need a Docker file. In the Apptainer world, you need what's called a definition file. And a definition file has several different parts to it. It has a header, and then it has different sections that most of them are just like shell scriptlets. So let me go ahead and write this container definition file really quick. The header starts with a specification of the Bootstrap agent that you're going to use. There are lots of different Bootstrap agents that allow you to start your container from different sources. You can start your containers from operating system mirrors. You can start them from local containers that you have saved on your system. There's lots of different ones. Just for simplicity here, I'm going to start a container from Docker Hub because that's something most people are kind of familiar with. But yeah, just bear in mind that there's a lot of flexibility here. I'm going to start this container from Rocky Linux 8. And then this section post, basically this is what installs everything into your container. So post means after, and it's saying after you download this container, shell into it and execute all the commands that I'm going to give you here in post inside the container. So I'm going to do a DNF update. I'm going to install a bunch of packages that I think would be interesting and useful to have inside the container. Vim, wget, get Python 3. Python 3 is important because I'm going to be installing this Askinema program that I'm going to kind of demo for you briefly. And I need pip. And then I'm going to do a pip 3 install Askinema. And I'm also going to give this a run script. If you remember previously, I said that there is metadata inside the container, which tells the container what to do when you run it. Well, this is that metadata. And so I'm going to specify that we should execute Askinema, and we should do so with whatever input the user gives it. Now, I'm going to build this container. And once again, I want you to bear in mind that I am an unprivileged user using an unprivileged installation of Apptainer, and I'm supplying no privileges to this build command whatsoever. And so you might expect that when we get to like the DNF update and things like that, that's not actually going to work. But as you can see, that's actually working just fine with no trouble. And even if we kind of keep our eyes here on this output and kind of watch, you're going to see that pip is now angry with me because it says that I'm running pip as root. And that's completely because I'm using the user namespace, and Apptainer on my behalf knows that when I build a container, I need to do so as root. And so it's pivoting me into this new namespace where my UID on the host system is being mapped to UID 0 inside the container, so I can do all this in the container. And that all just kind of works now. Okay, and so just to kind of round that out, I now have this new file called askinema.sif, which I've just created. And I can, let me go ahead and just run it, because I just told you that SIF files are executable. And you can see that here's the, so that just gives me the help. And because I used, I created that run script, because I did that, I can just go ahead and run this and get the help out of it. So Askinema says that I can use the record subcommand to record a terminal session, and I can use the play subcommand to play it back. Let me just go ahead and, for fun, kind of demo that to you. So I'm going to record. And what this does under the hood is it creates a JSON file, and it just uses that JSON as a recording of what you did. And I'm getting a little warning here about one API. I'm going to explain that in a second. Just don't worry about that for a second. Let me do a who am I. Remember, I'm in the container right now because once I executed that command, it popped me into that container. Okay, I'm just going to go ahead and exit. So even though I was inside the container, I was still the same user that I am on the host system. And actually notice that I even have the same UID, right? So I'm UID 1234. If I look at my current working directory, so I saved this file demo.json, and if I look at my current working directory, I can see that I actually saved that file into my current working directory, and notice that it's actually owned by me. And this is one of the really useful side effects of the privilege model that Apptainer has, is that number one, I'm the same user with the same UID inside the container as I am outside. And number two, this directory was automatically bi-mounted for me into the container at runtime so that I can still write out to the host system. I can read from the host system and so on. And so I'm going to go ahead and use this container again to read from the host system. I'm going to use the play command within Eskinema, and I'm going to play that demo.json that I just created. And so now this is why Eskinema is kind of neat, is it's going to play back. I'm not actually typing anything, look, no hands, and it's going to play back the recording that I just made. Just by the way, while we're talking about this, Eskinema is a pretty cool tool that you can use sometimes. You can embed these Eskinema sessions into your web pages for documentation, and you can use these to kind of show users what you're doing and send them to users and so on. And so that's kind of a cool little tool. Okay, so I'm gonna go through so maybe now is a good time. So now I'm gonna kind of transition a little bit. This is a basic look and feel of Apptainer. I'm going to transition at this point into two slightly more complicated and slightly more advanced examples. And so maybe now is a good time to kind of stop and ask users or ask anybody in the in the session if they have any questions. You guys hear me okay?
Yeah. Do you see the chat? I don't see anything in Q&A, but if you see in chat, there's a couple questions. One in terms of covering security implications.
I actually don't see the questions because I'm sharing my screen. I wonder if
let me help you out.
That'd be great.
Okay. All right. So the first one I see is, do you cover security implications or SE Linux?
Am I going to cover security implications of SE Linux, or I don't understand the question. I'm sorry.
So Apptainer gives you a lot of cool flexibility, but end users have not a scalpel, they have a sledgehammer. And I'm wondering if you have to prevent people from doing this sort of thing, are you covering that? And how does this play with SE Linux? If SE Linux is enabled, does this break?
Okay, yeah.
Wondering if you're covering that.
So SE Linux, no, this doesn't break if you're using SE Linux. So I have, to the best of my knowledge, I have SE Linux enabled on this system, here. If you're concerned about the security implications of allowing users to use the user namespace, maybe is that kind of the crux of your question? And you'd like to, sorry, go ahead.
Yeah, I just wondered if security was going to come up as a topic.
Yeah, so, right. It wasn't going to come up, but I can bring it up briefly. Traditionally, the way that Singularity and Apptainer, so backing up, there are a few operations within Singularity / Apptainer that require privilege, right? And the main, operation that you're going to come across anytime you use a container is that you've got to mount that container to your host system. And so the way that we're doing that now to enable users to do this is by using squash fuse. So that fuse file system is what allows you to mount your file system, your container file system, to the underlying host file system. Now, as far as using like the user namespace in order to set this up, and then also to be root inside the container. So it used to be that we would use, and you can still install Apptainer in such a way to use an SUID workflow. But the trouble with that is that, and the Apptainer developers are very smart people and very careful people, and they've done a very good job. But obviously, it's very, very difficult to police an SUID workflow and to make sure that there's no way, even though you're granting the user root permissions for a second to carry out one specific operation, it can be really difficult to lock that down and to make sure that there's no little sneaky privilege escalation pathway that exists there. And like I said, I mean, the Singularity and Apptainer developers have done a really good job at that, but it's kind of a smaller group of people. It's kind of a smaller community of people that are looking at that than the user namespace, which is a kernel feature. So what we're doing now with this is we're basically offloading all those security implications off of the Apptainer developers, and we're onloading those onto the kernel developers who are responsible for developing user namespaces and the within the kernel itself. That's a much larger community. So I think that we generally think that this is this is actually a more secure option, and this is a better way to carry these operations out. I will say that there have been some CVEs reported associated with the user namespace. Historically, that's why they weren't enabled by default in Enterprise Linux 7. But they're enabled by default now in Enterprise Linux 8. And I think that from what I've heard within the Apptainer community, most of those CVEs have had to do with utilizing the user namespace in combination with the network namespace. So we suggest that if you're really concerned about users trying to exploit user namespaces to gain some privilege or to figure out some sort of escalation pathway which is not reported yet, probably what you should do is disable network namespaces, which are probably not really used very much within Apptainer or within HPC context as is. Does that kind of go to toward answering your question a little bit, Mark, or is that the kind of discussion you were talking about having?
Yeah, I've got a user pestering me at the same time I'm listening to you, so it's good this is being recorded. But yeah, that's good information.
Okay, cool.
So
Awesome.
I got another question here. Is there any reason not to run Apptainer 1.1.5?
Any reason not to run Apptainer 1.1.5?
Correct.
No, I mean, that's the version that I'm running here. 1.1.6, I think, came out yesterday, so maybe that's a reason not to run 1.1.5. But yeah, I mean, I created this demo and everything using 1.1.5, and so I didn't want to switch last minute and then have something silly occur. But no, I think that it's fine to run that.
Okay. And then it looks like Keith is he's implemented some containers on his cluster. He started to publicize his show how customers could pull down containers, and then his security guides, got into the mix of things. He said it's no different than source code from GitHub, but they're concerned there are many spots in an image to have malware scripts. What mechanisms do people implement to protect themselves here? What can be done to mitigate risk?
This is a complicated topic. And I can touch on it briefly, but really, if we were going to get into this topic in detail, it would take an entire, webinar. So, okay, his security folks, in one respect, are right. He's right, and his security folks are right. He's right that running a container is no different from getting code from GitHub. And his security folks are right because it's no different than getting code from GitHub, but every single code that you get within a container has, at least tens and maybe hundreds of megabytes of other code associated with it that also has to be, if you're going to be, if you need to audit stuff, that you also have to audit all that. So it's no different than getting code from GitHub. It's just a lot more of it, right? And so there are a lot more places that, malicious things could hide. Now, the way in which Apptainer works, it prevents you from running SUID bit programs or doing any privilege escalation of any type within the container. If you don't have any privileges, like if you can't escalate your privileges on the host system, or if you choose not to escalate your privileges when you enter the container, then you're locked down and you can't escalate privileges inside the container either. we have seen historically that renders some CVEs and some vulnerabilities and things that would normally be a problem on a host system, that renders them moot inside of a container. Because the privilege escalation pathway that you would use to take advantage of that don't exist within the container. So that makes things complicated, because that means you can't just scan your container for files that have been reported to contain CVEs and then get a list of all the CVEs and then mitigate them and say, okay, well, this container, because those may not be CVEs to begin with. And there's another issue, and that is that the way in which containers run means that there may be vulnerabilities within the container itself or within the runtime itself, which don't exist on the host system. So this is another reason why you can't just scan the container and say, oh, well, here's the reported CVEs, replace these files, and then this container will be good, because it might be that there are vulnerabilities which are not reported in the context of a host operating system. So container security becomes really, really complicated. And I think that, once again, this is a topic that we could talk about. I could go on for a really long time about, and I won't, because I've got other stuff to talk about, but sorry.
No, that's great to know. Okay.
Okay. I'll cut it there.
Sounds good. Thank you.
Are there any more questions, Brian?
I think there's, I think Sandra here is probably, adding on to the security portion here. So I'm just going to let these go, Sandra. I'm sorry.
Oh, actually, Brian, I'll present that one. So
Okay.
he's asking about the sub-UID, sub-GID files, etc sub-UID, and how the users are listed in there for containers. Are those still necessary? That's the question.
That's a good question.
And I can say on our Werewolf builds on Werewolf 4 and in OpenHPC, they're still used and replicated. That I can share. So when you add a user, it automatically adds them to sub-UID, sub-GID.
Yeah, and there was a little bit of context for this that Sandra was asking if you were using fake root. And I think the answer is you're not, that on the most recent version of Apptainer, it's just doing unprivileged user namespaces and doesn't actually use fake root. But the Apptainer documentation talks about sub-UID and sub-GID in a fake root context. So the question was if you still need to do that if you're not using fake root.
Yeah, and I'm following along as an unprivileged user on a Werewolf 4 OpenHPC cluster, and I'm able to do all the same things that David is doing without using fake root.
Yeah, and this is one of the reasons I'm hesitant to kind of delve into that question, is because there's been a lot of recent developments, and I'm actually not sure what the state of that is right now. So that Dr. Dave, who is the person who has done a lot of this work and has championed a lot of this work and pushed it forward, would really be the best person to talk to about that. That would be a good question to ask on the GitHub, in the issues on GitHub.
I noticed fake root screamed by when the build was happening on that, by the way.
Yeah, and I think that it depends a lot. It depends on, so there are a few different escalation. There's a few different code pathways that that Apptainer can go through, and it's going to depend on the configuration of your system and a lot of other things as far as what code pathway it actually chooses. So I'm not totally sure. I hesitate to answer that question right now because I might give you the wrong answer. All right, there's two other things I want to copy here, or I want to kind of go through before I hand it over to Jonathan, and he's going to talk in depth about interactions between MPI and containerization. But one of those, the first one, the kind of in-depth thing I want to go through, is I want to talk about how you as an administrator maybe, or you as a user, can install software on your system, and you can make it look like it's an installation which is bare metal, but it's actually just a container install, and how convenient that is. So in order to kind of show this, I've got this this directory here called SAM tools. And this is one of those things you're not going to really be able to follow along with this so much because you'd have to create a bunch of files and everything. But if you're interested in doing this on your own, if you go to GitHub and you look for the NIH HPC, this is the place I used to work. And we published a lot of Singularity definition files, and we published basically the method for installing all these on your system, as though they were just installed on bare metal. And so I'm going to kind of go through an example and show you what this looks like. So if I go into the SAM tools, so SAM tools, I should preface for people who are not like into the biosciences, SAM tools is a really widely used tools for omics, for genomics kinds of research. And I'll just leave it at that because that's about the depth of my understanding. So I'm going to go ahead and CD into this directory, and you can see that I've got a version here. So it's kind of set up like you would set up an installation if you were going to use like a module system like LMOD. And then underneath of that, I've got, this should look pretty standard. I've got a bin directory and a libexec directory, and I've got some source for the source code. So you might expect that if I look here in the bin directory, I'll have a bunch of compiled binaries. If I look here in the libexec, I'll have a bunch of libraries, and then in the source, I'll have some source code. But that's actually not what I have, right? If you look in the bin directory, all I've got is a bunch of symlinks. There's nothing in this bin directory that is not a symlink. And all these symlinks just point directly to this wrapper.sh script. And so let's look and see what that wrapper.sh script is doing. And then you'll also notice here in this libexec directory that I have a container. I have just something called app.sif. It's a sif file. It's a container. Okay, so let's look at wrapper.sh. So this is a very short little script, but it's doing a lot of work. And so I'll go through, basically it's using introspection. It's saying, where am I? What is the directory that I'm currently in? And then, assign that to the directory environment variable. What image do I have access to? What's the container image that I have access to? In this case, it's just app.sif, that one I just showed you. And then this one is a little bit confusing because it's like, what command was I invoked with? And this is where people sometimes get tripped up. You might think that this is just always going to resolve to wrapper.sh, but the trick is, and the reason all this stuff works, is that it's not. This CMD is going to resolve to whatever command was used to invoke the wrapper. Even if it's a symlink, it'll resolve to whatever the symlink is named. So because of that, and so then it comes down here and it actually does an Apptainer call, right? It does an Apptainer exec in the directory that I'm currently at. I expect to find an image, and then I'm going to give it whatever command I was invoked in along with the command line. And so what this allows you to do, let's say I want to run SAM tools. SAM tools is symlinked to this wrapper. So when I run it, when we get into the wrapper, when it gets to this point and checks out that command is going to resolve to SAM tools. And then it's going to say Apptainer exec, that image, SAM tools, and whatever command line that I gave it, go ahead and pass that right off to SAM tools. This allows me to do things like just run SAM tools. And I'm going to run it with help. And you can see that just works. So what's inside this container? So if I look again, I've got this source here, and that's got a definition file for the container. If I look in that, basically this is just a SAM tools container downloaded directly from biocontainers. This is a organization that has this container up on Docker Hub, and then I just installed Perl inside of it. Okay, so you can hand this off actually to your users, and you can allow them to run code from a directory which is organized like this. And one of the things that allows you to do this is you've got this environment variable here that you can use to set whatever directories on the host system that the user is supposed to have access to, you can bind mount those through this wrapper script at runtime when the user runs it. And so wherever the user has read and write access on your system, they're going to go ahead and have read and write access when they're running these programs as well, if you set that up appropriately. You can also inject environment variables at runtime. In this case, I've injected lcall equals C because I want the, the container to run Perl, and I don't want it to give me warnings about the locale. And setting your containers up in this way allows you also to, you can use lmod or any other module system in order to control this container installation just the same way. You just add this bin directory to your container, your user's environment, and then they would have access to all these different commands. And in fact, this is relocatable too. So you can just take this directory and you can just tar it up, and you can move it to another location on the system. It even works across operating systems, right? So say I'm upgrading from Rocky 8 to Rocky 9. I've got a lot of things I've installed. I don't want to like reinstall everything. That's okay. If you're going to install Apptainer on your system, you can just tar these directories up and move them to your new installation. And once you untar them, they're going to work just the same. So this is a really convenient way to install this software and manage this software. And it's something that the NIH has been using and does use to manage hundreds of applications on behalf of users. Okay, and so now I guess I'll ask if there's any more questions. I'm going to move on to the final portion of the talk, which is going to be an extended example of using a new tool called OpenRadioss, which Altair recently published. And I'm going to talk about a community collaboration, which has been occurring between CIQ and Altair and Intel to really push this science forward. So as I'm preparing for that, is there any more questions?
Nothing on the queue right now, David.
Cool, thank you. Okay. I gotta find where I put my slides. Okay, here. Sorry. All right. So we're going to start talking about OpenRadioss. So what is OpenRadioss? Okay, so Altair has been publishing for a long time some software called Radioss. And if you're not familiar with this, Radioss, I might not describe it as accurately as I could, but Radioss is a analytical system that allows you to do things like model different materials and model different components of a larger system, and then model how those materials and components are going to like deform under stress, or how they're going to behave as the environment changes or whatever. And in practice, what this is often used for is in the automotive industry, and not just the automotive industry, but in others. But just to give a concrete example, in the automotive industry, Radioss is used quite frequently to model car crashes and things like that. And so it's been around for decades. It's a very important software because, if you're riding around in a car, chances are it's probably there's been modeling efforts to show how it's going to react in a crash and to make sure it's safe. And it also saves the automotive industry and other industries tons of money because, like, instead of actually going out and crashing vehicles, they can run many simulations of crashing these vehicles in software instead, and get a lot of information from that. So last year, Altair announced that it was going to create an open source project based on Radioss called OpenRadioss. Okay, so here at CIQ, we've got some people who are really plugged into new emerging technology, and they immediately said, wow, this is a huge thing. This has been closed source for decades, and now it's becoming open source, and we now have a tremendous chance to help the open source community and push this forward by containerizing and documenting how to run this. And so one of my colleagues, Yoshiaki Senda at CIQ, who's another application engineer, he actually took this and ran with it, and just within, it was like a matter of days, he had this containerized. and he had a pull request in upstream to Altair's GitHub repo where OpenRadioss exists, and it was just really taken off. Intel very quickly began to take notice of this work, and they said, wow, we could help to optimize that with our new, we were talking like a few minutes ago about one API. We could really help to optimize the MPI portion of that with one API, and we could really help to push this forward as well. And so what's emerged from this is this really great community collaboration between these three different entities, which has produced a really nice containerized portable version of OpenRadioss that you can, you can take anywhere and you can run and you can develop and look at. All right, so I'm going to show that a little bit later. So let me just go ahead and give you an idea of, and oh, by the way, once again, this is going to be hard to follow along with in real time. But if you just go to Google and you Google CIQ OpenRadioss, you're going to find lots of blog posts and press releases and things of that nature. And if you just click on some of those, you'll find this blog post or a similar one, which is going to give you step-by-step instructions for obtaining all the stuff that you need to go through this demo, and for all the actual commands and steps and everything that you need to recreate this. So if you're interested in this, there's a way for you to recapitulate this. Okay. I'm going to step up into my demo directory, and I've got this subdirectory here called OpenRadioss. If I CD into it, I've got two subdirectories. One of those is the GitHub repo for OpenRadioss, and the other one I'll look at here in a minute. So let me go into this GitHub repo. If you download the GitHub repo, you're going to find that there's a directory called Apptainer. And if you CD into that, here, let me bring this to the top of the screen again. If you CD into that, you're going to see that there's this definition file for the Intel one API version. And I've gone ahead and I've created that already. I'm getting kind of short on time, so I'm not going to spend too much time. I'll just go through really quickly and show this to you. So this starts off from a Rocky 9 container, and then I'm not going to go in detail about this. Basically, this file is going to add the repo for the Intel One API stuff that you can install, so that you can use a DNF command to install it all. And there's a section here which is going to install a bunch of like compiler toolchain sort of things and dependencies. There's some stuff down here which is going to get the source code. And then there are commands down here to set up the environment and actually compile the code. And so this container takes a little while to build because you're actually compiling everything from source. Then there's a section that sets up the environment for runtime. And then there's a run script, which just says basically however you invoke me, I'm going to go ahead and run whatever you tell me inside the container. This is a pretty nice and simple little run script. All right, so that's really quickly kind of whirlwind what this definition file will build. And then the top level up here, there's this 2010 Toyota Yaris directory that I'm going to CD into. And essentially, I'm leaving out a lot of details in describing this, but essentially what this directory contains is a model of a 2010 Toyota Yaris with all of its components, with its engine, and all that stuff, a model of a wall, and the instructions for how to crash the Yaris into the wall. And this is what we're going to do is we're going to calculate, what that crash looks like, and we're going to go through the actual calculations in order to make that crash happen. Okay, so there's two commands that I have to run. The first one sets this problem up, and then the second one is the one that actually, carries out the MPI implementation and actually does the crash. So I'm going to run the first thing. So remember, I've got that, I've got this CIF file here, and I can just invoke it, just by giving it a relative path to it. And then after I do that, within the container, there's this program called Starter Linux 64 Intel, and that's the Intel compiled version of this program. And then I'm going to give it as input this Yaris OpenRadioss.key. Remember that my current working directory is available to me by default with Apptainer. And then I'm going to give it the number of processes is going to be 8. And so what this is going to do is it's going to take this model and these instructions that I have here in this directory, and it's going to take this problem and it's going to split it up into 8 different parts. And it's essentially going to set this up in such a way that it can be run in parallel. We can parallelize it. Okay, so that's going to take just a second to do its thing. And it's giving me a lot of warnings here about different materials and, you know, things that are maybe not optimized the way that they ought to be within the model. I kind of think that this is sort of similar to the way in which your compiler might give you warnings about, you know, things which are not like perfect within your C code, but they're not actually errors. They're just, you know, you could do a little bit better with this material. You could maybe do a little bit better with this component and so on. Okay, so that's done. And what it did is it created these 8 different RST files. So in the interest of time, I'm just going to go ahead and copy and paste the next command. And this is going to set Jonathan up too for his portion of the demo, which is coming up next. Here, I'm invoking this MPI run. I told you earlier, I had a little warning when I entered the container that said that I had some MPI libraries which didn't exist. That was because it was sourcing my .bashrc file when I ran that, and my .bashrc sets up some environment for my MPI run. So that's what that was all about. In any case, I'm going to invoke MPI run with 8 processes. I'm going to use this container, and you know, so here, this model that I'm using, I've got MPI installed on my host, and that's going to match what's in the container. This is known as the hybrid model. And Jonathan's going to show you some stuff next, which is going to be really cool, which is going to show you how you can do things completely containerized and just leave the MPI libraries off of your host altogether. But for right now, I'm going to go ahead and run this. So, you know, MPI run on the container command, and it's going to start running. If I go here into my activity monitor, it's just a really simple little way that I can show you. I've got 8 CPUs running. So I have 10 CPUs available to me in this virtual machine. 8 of them are, you know, running this demo. And this model, unfortunately, on my little low powered machine that I'm using here, would take many, many hours to finish. So I'm not going to show you all the way through, obviously, it being finished, but I'll show you when you're done. Here's like one of the things that you're going to get. So we'll get at different time steps, you know, what it looks like for this car to be crashed. And you can, you know, spin this around and look at this, and you can change the opacity so you can see the different materials which are in this model. So it's a lot of different materials that you're, you know, that you're deforming and looking at in relation to one another. And now I'll show you, just to finish up, if I can find my slides once again. Oh, yeah. So this is kind of the final bit here. This is an animation that Yoshiaki Senda put together and shows the final result of this crash simulation using this containerized version of OpenRadioss. So, okay, that's all the stuff that I wanted to demo today. As far as Apptainer goes, I'll be back later on to talk about container orchestration and things along those lines. But at this point, I guess I'd like to take any more remaining questions that I've got about this section, and then I'll pass things over to Jonathan Anderson, who's going to talk about MPI and everything related to MPI within containers.
Thanks, David. I currently don't see any new questions that have come in. So if we want to go ahead and just proceed, and then as they come in, you can answer them.
Sounds good.
All right, Jonathan, you up?
Yeah. All right. Just a few preparatory things here. All right, everyone. Can you hear me okay?
Yep, absolutely.
Yeah, okay, great. Well, thanks for coming. And thanks, Dave, for all of that information about Apptainer. And we'll get more later. And I also wanted to say thanks so much to Steve Jones for sending some kind words our way. I'm with CIQ. I'm a solutions architect there, and I'm pretty happy about the work that we're doing. But I'm glad to hear that it's being noticed, and then also wanted to thank NVIDIA for its support and sponsorship in this program. So my background is mostly in academic high-performance computing. I've worked a little bit in the U.S. national lab space and also in the higher education space. And I am going to talk about how my perspective on the best way to containerize MPI applications, mostly with Apptainer. But we're going to talk about it kind of a little bit at a higher level for a moment as well. So Dave has been talking a lot about Apptainer and showing us how it enables us to build these portable and containerized applications in a way that's suitable for HPC. But if you are familiar with containerization at all, you've probably heard of Docker. And I'd like to start by contrasting part of the Docker experience with the experience of using containerization in HPC today, or at least my experience of it, and something that I've noticed. So one of the best things about Docker is the community and coordination that exists around Docker Hub as a popular container registry for OCI and Docker style containers. So containerization, particularly in the Docker ecosystem, drastically simplifies the deployment of these large complex systems built out of multiple services in enterprise services contexts. For many applications, someone else, maybe even the developer of that application, has already built a container for you, and it's just sitting there in a registry, and you can pull it and use it. And it's also been a huge boon for software developers. Just locally, they can develop a container definition and test their software in a repeatable, the same environment over and over again. Before containers, it would be common for a developer to just be running their software and testing it on their local development machine, and that machine has state and it mutates over time, and that's a source of jitter and bugs. And so having these easily buildable and destroyable containers makes the testing process much more repeatable. But then also those containers can be published, and you can download that container and run the application in exactly the same environment that the developer published it in. But despite how popular, at least as we've seen, Apptainer and before it Singularity have been among HPC users, most people aren't doing the same with large, complex HPC applications, especially MPI applications. People don't typically download, someone mentioned OpenFOAM. They don't download that and then just run it immediately. NVIDIA does have, you've probably seen this really popular NGC container registry that seems mostly popular for AI and ML workloads. But by my observation, most of the people who are using that, their workloads are about these big, really thick single node, maybe multi-GPU, many multi-process, but generally speaking, non-distributed application use cases. And from my perspective, the biggest thing that's holding HPC applications back from like the same kind of broader adoption of containerization kind of across the industry is the confusing state of containerization for MPI applications. And it's all well and good to have an OpenFOAM container or a GROMACS container or an OpenRadioss container like Dave showed us. But if you can't just take that container and use it in a distributed kind of traditional classical HPC sense where it's running on a cluster of compute all orchestrated together, you can't really do HPC with it. So to understand the nature of this problem, I think it's useful to break down MPI into a few constituent parts and really get into the details of what we mean when we talk about MPI. So here I've got a really simple block diagram that I put together to point out and talk about. You start out on the left, you've got your MPI application source. A lot of this is still very research code, but even it all starts sourced somewhere. And typically you compile this with a command like mpicc. There's also like mpIC++ and mpifort. And these are compiler wrappers that understand how to talk to one of a number of compilers, but then also link in the MPI libraries that your application is written against. So your application will be written against the MPI specification, the MPI standard, and then you'll compile in libraries for a given MPI implementation. And then finally, you typically launch your application with either an MPI exec command or an MPI run command. These are different points along the standardization timeline of MPI. But that program will then reach out to a set of compute nodes. Often it's just SSHing across the nodes that are listed in a text file, or maybe that it got from its resource manager like Slurm or something like that. And it starts your application on the nodes, assigning a rank to each one that uniquely identifies the different tasks that are running and tells them how to contact each other over the network or an interconnect of some kind. So these three components here that I've called out are what I'll broadly refer to as an MPI implementation. The compiler wrapper, the MPI libraries themselves that implement MPI, and the launcher application that does process management. And these are usually bundled together and are very tightly coupled. You use, let's say, mpitch. You use an mpitch compiler wrapper to compile your application. It links in mpitch libraries, and then you need to use the mpitch MPI run or MPI exec command to launch it. The same is true if you're using OpenMPI or Intel MPI or MVPitch, someone mentioned earlier, or any other MPI. This is kind of the standard way that this works. And so it's definitely true that these three components are tightly coupled and proprietary within an implementation of MPI, but it's often it's often the case that you can't even cross versions. If you upgrade OpenMPI, generally speaking, people will recompile their application to bring in the new version of the libraries. In theory, they're dynamically linked, but generally speaking, you're advised to recompile your application, and then you'll launch it with the same with the MPI run or MPI exec that comes with that new version of the MPI that you've deployed. So with that understanding of what MPI is, let's try to containerize it and see what happens. So I like to build scientific applications with a utility called SPAC, especially MPI applications that tend to pull in increasingly large sets of dependencies. And again, more towards that repeatability mindset of making sure, one, that the demo works the same way that I built it. So SPAC is a source-based package manager. If you've used like BSD ports or Gentoo or something like that, it's similar, but it has a few features that make it really good for scientific software. First, it supports mixing and matching alternative libraries when you're building your application, and it can even handle multiple versions of a given application or library simultaneously. So you can use it just for yourself, or you can use it to deploy the software for kind of a larger cluster environment for multiple users. And second, SPAC has a containerize feature that builds application containers really efficiently. And so we're going to take advantage of that here. So this file that I have the text up for is a bit of YAML that defines what SPAC calls an environment. And so most simply, that would just be this top section that defines what packages I want to be in my SPAC environment through a set of specs. These are very simple specs, just the name of the package, but you can have other metadata here that tells it how you want each of these to be built. But this environment also contains a container definition that says how I would want to build a container that contains this environment. And this container is going to be an OpenMPI based container, and we're going to build the OSU micro benchmarks suite of benchmarks that I like to use in an environment like this as one step better than a hello world to show MPI communication working in this environment, though it also contains a hello world like application inside of it. So for this portion, I'll switch over to a live system so that you can see as much of it running live as possible. Let's see, cool. So I think it looks like we've switched over to my terminal here. I'm demoing today in an environment that we have access to as part of a collaboration, frankly, targeted at this work with Dell. So I want to give a brief thanks to Dell for supporting this work and for making this hardware available to us. This is a little 4-node cluster that is using OmniPath for its interconnect. Oh, I'm not in the right directory, so just a moment. This is in workflows and the testing tools and great. So from that SPAC environment file that I also have here, SPAC containerize, the SPAC containerize command generates an Apptainer definition file. It supports Docker container definitions as well, but we're using the Singularity as it's listed here format. So we can just run SPAC containerize. Let's see if SPAC is, oh, yeah. We'll load SPAC in. All right, there's SPAC containerize. So it's actually a pretty cool definition file too that it builds. Dave didn't get into this part of Apptainer's capability, but it has support for what it calls multi-stage builds. So we see that we have a build stage up here, and this is where it pulls a starter container image that has SPAC in it, and then builds our software that we want. But then at the end, we have a final stage that it copies the built software into from the build stage. And so this gives us really efficient small little containers with, all of that with the separation there. The build dependencies stay in the build container and get discarded, but only the finally built software ends up in the final container. So we can use that generated definition to build a new OSU microbenchmarks CIF image. The way I tend to do this is to say build. I am going to specify fake root here because it is my habit. I think that the version I'm on right now wouldn't work without it, but I haven't updated this environment in a little bit. And then you could like run SPAC containerize and export this output into a file and just put that file here. But I also often will just use an input redirect here. This is a bashism. And so Apptainer build will start building a container as defined by that SPAC container, SPAC containerize definition file. So this will take a while because unlike a lot of containers that you might build, it's doing everything from source here. So rather than wait for it, I have one. I'm just going to CC out of this. And we'll use one that I have prepared ahead of time. So that should be this. Oh yeah, I have a directory here full of CIFs. So we'll use some of these others as well as part of the demo. But for right now, we're going to be working with this OSU microbenchmarks.cif. And to my point earlier, this container here is 113 meg, which includes a base CentOS stream image. We're working on support for Rocky Linux in this environment as well. I have a pull request up to SPAC to do that. But for now, we're on CentOS stream 9, I think, actually. And we have OSU microbenchmarks and OpenMPI installed in there in this tiny little 113 meg container, which seems pretty good to me. So Dave showed us this before, but we can shell into this container. And from here, we can see that we have MPI exec available. And so we see we have this, the OpenRTE is the kind of broad name for OpenMPI's process management. So we have the OpenRTE version of MPI exec available from our OpenMPI implementation. And we have our OSU Hello application. These applications actually can run just by themselves. So we have that here. So what if we just tried to launch our application from here? So this host file that I also have lying around here, it is indicating 3 compute nodes. I think I left the 4th one out because it's in kind of a weird state right now. But we have a host file that lists these 3 nodes. We can say MPI exec host file, pass it that host file. We want to run 2 of them, which will be kind of a minimal test case for MPI working. And we want to run our OSU Hello application. So in a typical bare metal environment, this should work. MPI exec will SSH over to 2 of the nodes and start a process over there, and then use that process to invoke OSU Hello with ranks and configuration. But it does not work here. And we can see actually it printed the error in a different order than I've seen before, but that's all right. We see that it's unable to talk to node C5. I think it's complaining about C5 just because that's the first one in the list. And we have this other error down here that says it's unable to talk to ORTED or ORTED, which is the kind of remote side part of OpenRTE in a typical OpenMPI process management deployment. So there's one other thing we can try. We can try to do this without a shell. Like Dave showed, we can execute containers as executables. So if we did like sif OSU microbenchmarks.sif, we can run MPI exec version here, just like we saw inside of the container. And we can run OSU Hello. But if I try to do the same thing and just say MPI exec host file, get my host file there, say n2, and then maybe we even, now we're not inside the container anymore, so we don't have the OSU hello command here. So maybe we tell it, and you're going to need to look inside of this container and run OSU hello like that. So maybe this would work. Oh, it definitely helps if you, or it should help at least a little bit if you write the commands correctly. But we get the same error. We see it's unable to talk to C5. And if we scroll up a little bit, this is where I'm used to seeing this. We see we're getting the same error as well, that it's unable to talk to ORTED. And this is happening on the remote side. So let's talk a bit about why this isn't working. And I'll switch over to my slides again for a bit. See some chat stuff here. See if there's a question. Okay, no. Notes here. So when MPI exec runs, it uses SSH to connect to each remote node to start the remote process on that node. So OpenMPI is trying to use ORTED to establish that initial connection. So it SSHs over, starts ORTED on each node. And then that process establishes the communication with the starter process and configures that process with its rank and whatnot, and then execs into your MPI application. But that daemon, ORTED, is inside the container in our environment, not outside of the container. So it doesn't know how to access it when SSH is over. Because the SSH that we're connecting to, the SSH daemon that we're connecting to, is outside the container, not inside the container. So this container boundary problem where the MPI exec on your submit host is talking to, from inside the container, is talking to a different environment. It's kind of like if you're in a traditional HPC environment and you didn't have your shared file system set up correctly. You have MPI on the calling side, but not the compute node. I've tried to do some hacky things in the past to work around this, where I passed an inline wrapper script through the launch agent configuration parameter to OpenMPI to tell it to look inside the container for ORTED, but it just kept getting increasingly esoteric and weird error conditions and things. So I started looking for other options. So the Apptainer documentation has a whole page. If you go to apptainer.org and search for MPI, you'll get a whole topic here on Apptainer and MPI. And Dave referred to this earlier. There are two kind of historic approaches to this. One is the hybrid model, which ISS is the more popular of the two, and the bind model. And these are the same advice that we've been giving out ever since Apptainer was called Singularity. And people have been doing it this way for a while now, and this works. But I think that this is the crux of where we kind of let the complexity get away from us, and it scares people away from just expecting to be able to pull down a container and run it on an MPI system. So let's look at these two options. So the hybrid model uses the host's MPI outside the container to launch containerized MPI processes. And this requires that the MPI implementation on the host matches the MPI that's used by the containerized application. So you have an MPI run or an MPI exec on your host, and you MPI run or MPI exec the container itself, usually as an executable. And it eventually turns into an MPI process inside the container, but it's required that those be in pretty close alignment. Definitely the same MPI implementation, probably the same version. So what you end up with is the end user having to carefully guarantee and coordinate those versions between the local sysadmin and the application that they're bringing in. The bind model is a little bit more complex, especially from a systems perspective. It expects to kind of omit MPI inside the container and bind in the MPI application, or sorry, the MPI implementation that's on the host for dynamic linking at runtime. But you can still have issues if you build against one version of an MPI and then try and bind in a different version. And certainly this still doesn't work if you built against, let's say, MPitch, and then you try and bind in OpenMPI. So both of these historical approaches to this problem require, careful management of MPI compatibility between the container environment and the host, often down to a specific version. And in practice, this doesn't end up meaning that, a software developer publishes a huge matrix of available OpenMPI builds for their application up on Docker Hub or something. They just don't, or they do, but people don't pull them down and use them that way. So what typically happens is you just, even if you're doing containerization, you're pulling down software and building it seemingly like I did here, and building it against an MPI that's on your system, or you're building it against the same version of the MPI that's on your system, and then using it typically in that hybrid model. But to me, this conceptually negates many of the benefits of container distribution, because you can't just have this one size fits most container that's up there as a really solid production ready example that you can pull down and get started and use immediately for these broad MPI applications. But MPI exec and MPI run are not the only way to manage processes for MPI. So in the meantime, while some of us weren't paying attention, the MPI community has been developing a standardized process management interface, or PMI, starting, as far as I can tell, with this initial publication in 2010, mostly from Argonne National Lab, I think. This effort has produced a series of APIs. These are generally referred to as PMI1, PMI2, and now PMI-X. Though PMI-X itself is a kind of a new standard that replaces PMI in general and has multiple versions itself. These process management standards are supported by most modern MPI implementations. I think actually all of the MPI implementations, and multiple resource managers. Maybe not quite as many of them, but the ones that you would use. So using a standardized PMI interface removes the dependency on a proprietary PMI run or PMI exec application that's tied to that MPI implementation. Instead of needing to ensure that your containerized application uses a specific MPI implementation, you just need to document what PMI interface it supports. And again, from my perspective, requiring a site to support one of a set of standardized APIs is a much more reasonable prospect long-term than requiring that you have all of these different versions of different implementations of MPI available. So this environment that I'm running my demos in is a Werewolf 4 cluster, and Werewolf 4 lets you define compute node images using an OCI container file. And unfortunately, contrary to some comments earlier, we aren't planning on going into a lot of detail about this process, but I'll talk through it here. So this example container file here is pretty minimal. It installs slurmd and munge from OpenHPC. It installs Apptainer from EPEL, and it installs Rocky Linux's built-in support for Omnipath and InfiniBand. But that's about it. There's other stuff like setting up like NTP and things like that, but that's all that's in here. And notably, there's no MPI installed in this image. If you SSH over to this compute node, there's no MPI exec, MPI run, there's no MPI installed at all. And it's not coming in over a shared file system either. And we shouldn't need one because we're only going to use the MPI that's inside the container. And instead of using MPI for process management, we're going to use the PMI support that's built into Slurm. So here's what our new process management flow will look like. So we're going to use srun, which is a command that comes with Slurm, rather than MPI run or MPI exec, to tell Slurm how we want our MPI application to run. And srun will communicate with the Slurm daemon, slurmd, on the compute node, on the targeted compute nodes. And slurmd in this flow takes the place of Orted for doing that kind of remote side process management. So slurmd acts as what's called a PMI server, and then the MPI applications are PMI clients, and it does the configuration of that process, assigns their rank, tells them how to talk to each other, that kind of thing. And since PMI is a series of standards rather than an implementation specific interface, it works regardless of the MPI implementation that you're using. So whether your application was built with OpenMPI or MPitch or MVAPitch or Intel MPI, anything that supports the PMI interface works in this mechanism. So we do have to adjust the container that we built before to support PMI. Really all that has to mean is adding this plus MPI to the end of OpenMPI to tell OpenMPI to be built with that support. The OpenMPI package in SPAC, this Boolean for PMI enables support for PMI1, PMI2, and PMI-X. But I've made a couple other changes to this container file to this SPAC environment file to just jump ahead to the good part. I've also told OpenMPI to build with libfabric. So we see here fabrics equaled OFI, and that would then bring in this libfabric dependency. And so I'm also telling libfabric then to build with support for sockets and TCP UDP, but then also PSM2, which is the interconnect that OmniPath will use, and verbs, which is the interconnect that would be used with an InfiniBand fabric, or if you're running like RDMA over converged Ethernet, that would use the verbs provider as well. And then we didn't get it in time for the demo. Dave and I were talking about support on Amazon's EFA and kind of a cloud environment. And there's an EFA thing here too that I just forgot to include. And the same container should work up there with EFA as well, but we just didn't get it. We didn't notice that I had omitted it in time. But yeah, the single container should support all of those fabrics without needing to rebuild them or rebuild the container. And because we enabled PMI support, it can be started by any PMI equipped resource manager. Yeah, so I think, yeah, it's time for switching back over to this demo environment again. So we're back here. So, okay, we'll clear this and we'll use, like I mentioned, Slurm's srun command. The nodes I'm running on are in a partition that designates them as OmniPath nodes. So we specify that. That's nothing to do with MPI, but just for this environment. We tell Slurm to use its PMI2, not MPI, PMI2 support for MPI. It has other MPI support mechanisms that both predate, and now there's also PMIX support in some Slurm builds, but we'll be targeting PMI2 here. We want to run 2 MPI tasks. We want to run one of them on each node, so this will pull in 2 nodes. And then we'll run OSU microbenchmarks. This PMI build that I, again, provided earlier, so we don't have to wait for it to build here in the demo. And we'll run OSU hello. And here, with that container, we now have a single MPI process, or that the terminology gets broken here, but we have a single MPI job, let's say, 2 processes, and they are each one running on a different node and communicating over MPI. But this hello world that comes with OSU is a little bit bare bones. I wish that it had extra verbosity, either in an option or here, that would say which nodes it was running on, because I look at this and I'm not confident as a sysadmin that it's doing the right thing. So I wrote this other hello world that will run so this is a different container that contains a hello world application that was actually, the way this container is built is it installs OpenMPI in the container and then brings in a .c and compiles it as part of that build step with MPI-CC. And then that gets copied into the final container as well. But we have this MPI hello world application. Come on, there we go. And so here we have some extra verbosity that says what node it's running on. We have, one of them's running on C5, one of them's running on C6, what rank they are. They are both happening to be run on the same CPU core. I wonder if Slurm actually tries to make that happen. It seems to happen every time I run this. And then for instances where you're running multiple tasks per node, I also included the namespace here, the mount namespace, so that you could see whether your processes were in the same, container name. I'm using mount namespace as a proxy for the idea of being in the same container. I think I did this in practice. Let me see if I can run 2 tasks per node. I hope I didn't just imagine this, and say that I want 4 tasks with 2 tasks per node. Yeah, so here now we have 2 that are running on C5 and 2 running on C6, 4 ranks. And we can see that these 2 ranks are also running in different container namespaces. And so they're different instances of the container. So we'll do a slightly more impactful case. So we'll go back to that OSU hello, and instead run OSU BW. This is the bandwidth test for that comes with the OSU microbenchmark suite. So we're using the same arguments to srun, the same container, just calling the OSU BW command instead of OSU hello. And if you do a little bit of math, we can see DC. I had to look up how to use desktop calculator here to do this quickly on the thing. But if this is megabytes per second. If we multiply this by 8 to see bits per second, we can see we're getting pretty good efficiency on a 100 gigabit fabric here. So we also, performance is one thing, but we want to confirm that it's running over the native OmniPath transport, that PSM2 that I talked about. Because we compiled OpenMPI against libfabric, we can use libfabric's options to inspect what it's doing. So the option for that for libfabric is FI log level. And I can just specify these as environments or as variables for this srun command, and they end up getting passed through srun to the remote process, even through the container, and affect the run of the containerized application. So we can set this to info, if I spell it right. We get a lot more output here. But notably, I'll actually search for it. So here we can see that the fabric that it ended up selecting is the PSM2 fabric for the communication transport between the nodes. Cool. So real quick, just to kind of drive the point home that this is a portable process that isn't dependent on any MPI implementation, I can also run this other container that I built in exactly the same way, except for I built it against mpitch. So this container is in a slightly different location. So OMB mpitch, and then I have OSU microbenchmarks. Then the version output for that is kind of long, so I'll just look at the top of it. So where before we saw the MPI exec was based on OpenRTE, mpitch's MPI exec is based on a system that they call Hydra. And so we see we're using that. Our MPI exec here is now Hydra instead of OpenRTE. And I can srun this. I'm just going to copy it in from here just to save some time. So same arguments, we're just switching to this other container that is using mpitch instead of OpenMPI. And there's a few error messages up here. I'm pretty sure this is a bug in Slurm. I did some Googling about it to try and figure out what was going on here, but it seems benign here. But we're getting similar performance. I think it's actually just a tiny bit better. With and I didn't have to do anything on the host. Again, neither of these MPI implementations are even installed on the host. Nothing at all. So let's switch back over here. So in the examples that I've been doing here on the system, I've been using PMI2 because I wanted to use the build of Slurm that was just in OpenHPC. And there was a little bit of conversation earlier about the broken state of PMIX in OpenHPC right now. The version of Slurm that's in OpenHPC doesn't have PMIX enabled, and I'm not certain why. And I think the original comment was that PMIX is broken in the version of OpenMPI that's in OpenHPC right now. That I don't know that, I haven't tested it, but again, the ones that I'm running here were built as part of that SPAC installation process during the container build. So I'm not using the OpenMPI builds of, or sorry, I'm not using the OpenHPC builds of OpenMPI or MPitch. I'm just building my own and putting them in the container. But the ecosystem has continued to evolve as part of the exascale effort, and that's where PMIX comes from. So my understanding, I'm not very much involved with this process. I'm still learning about PMIX, but my understanding is that as systems got larger for the exascale effort, the process of starting all of those MPI processes, let's imagine you're doing one per core on tens of thousands of compute nodes, let alone how many cores each of those nodes has. The process of starting them all from one process running on your submit node just didn't scale. So PMIX adds, as I understand it, a bunch of peer-to-peer communication between compute nodes to distribute out the information of which nodes have which ranks and how to talk to each other, that kind of thing. So this process should work just the same with PMIX. You just, well, the container that I built for OpenMPI should just work as is, because again, that Boolean should have enabled PMIX support. You just need a PMIX enabled resource manager. And if you don't have one, the PMIX project also includes a reference implementation of a PMIX server called PRRTE, or PRRTE. So you can use PRRTE to start MPI applications in environments where you don't already have PMIX support. You can even have like your resource manager start PRRTE and then use that to start PMIX applications if you want. So we've made mention of, Greg mentioned yesterday, and Dave is going to show here in a little bit, that at CIQ we're working on a platform called Fuzzball that we envision as the future of HPC for a lot of really cool reasons, frankly. And Fuzzball, among many things, has as part of its mission to couple the expectations around HPC performance and low latency communications, that kind of thing, with a lot of the practices like containerization that we associate with the kind of buzzwordy term of being cloud native. Fuzzball has a fundamentally different relationship with containers because of its architecture. Everything in Fuzzball is a container. And so as a result, you don't have that container boundary problem where you've SSH'd over to your remote compute node and now you're outside of the container. In Fuzzball, you're always inside of the container. So this isn't a practical problem for Fuzzball at all. The fact is, Fuzzball's MPI support to this point is mostly based around the traditional model of just using the implementations, MPI exec and MPI run process management stuff, because it just works, because all of the code is there everywhere to do that. But there are likely still performance benefits to using PMIX, at least, for process management as we deploy Fuzzball into kind of exascale scenarios. So I expect that will become a larger part of Fuzzball's MPI support in the future. And for typical HPC workloads, traditional MPI process management works just as well if all of the code is there. So if you're running in a Fuzzball environment, for the most part, this already was resolved for you. So from my perspective, with the stuff that I've learned putting this together in the first place, the future is really bright for MPI applications and containerizing them and simplifying the distribution and management of MPI applications for research, whether it's because of increased support in resource managers and MPI for PMI and PMIX and things like that, or the availability of discrete server implementations like PRRTE, or entirely new approaches to MPI process management like we have in Fuzzball. As all of these different approaches mature, I'm expecting that we'll see more popular HPC applications just sitting up in a container registry, and that it will become more normal over time for researchers rather than building them in a big pile of software on the host and the host environment to just pull an image down, run it immediately, and not have to deal with all of that. And the fact is, you can already do that today. You probably can in your environment. At the very most, you might have to enable support for PMI in your resource manager. So even if you're building your own containers today, I encourage you to start looking at running them this way. And it just makes it that much easier to share containers and move them around, bring them with you when you go to a different system. And it kind of breaks down that last big barrier between, or I shouldn't say the last, but a large barrier between kind of HPC software applications and the advancements that have happened in software development and software management, thanks to containerization and the likes of Docker and Docker Hub. So that's me. That's what I have to present. I'm really happy to take questions if there are any. Yeah.
Sorry, we do have one question. I don't know if when I share screen, I can't see the comments. I don't know if you have the same problem, but Mark has asked any comments on containers and very low level hardware CPU features, heterogeneous versus homogeneous hardware.
Yeah, so the most, so like the highest level place that this exists would be the emergence of ARM as a computing platform. So you can build containers. Most registries will support building multiple containers with targeting multiple CPUs, and then have those containers, like your system will pull down the right one. I don't think that registries today support building like different levels of x86 container that will then detect, oh, you have AVX 512 or you don't, and then pull down the right container. So if you were going to do that today, I expect you have basically two options. You can either build a bunch of named containers and say this is the AVX 12.1 or 512.1, or just target an architecture and name it that, or decide that you're not supporting CPUs before a certain instruction set. Or you can use functionality like the Intel compiler has the ability to bake multiple instruction set code paths into a single executable, and then it will detect CPU capabilities and branch based on what's available at runtime. But beyond that, like I think those are your options today. There's something similar in GCC. I think that the Intel compiler tends to wrap every instruction set like optimization around a detection thing, whereas GNU ends up building multiple binaries and then packing them together as one big super binary that has one branch at the beginning. But I think those are your main options, and you could put those into containers to make them universal in that way.
One thing that we, oh, sorry,
Jonathan. So sort of where I was going with the question was, I wondered if container use abstracts you away from getting any of the advantages of low-level CPU features.
I see.
And you've just answered the question by saying you can build them specifically for a certain architecture, which means obviously you have access to those features.
Yeah, and another thing that's worth considering, it's like almost as a side effect, by the way all of these containers get built, whether it's an OCI container and you have a Docker file or a container file, or it's a kind of native Apptainer definition file, they're all just these really minimal scripts of how to build your environment from nothing, or from a defined static upstream base. And so there's the one size fits most. I published this container and now you can pull it down and run it. And you can either try and make that as universal as possible, or you can document you must have at least this CPU to play. But you also, by virtue of doing that, have that definition file. And so my encouragement is, if you're publishing containers, always publish your container file also, because it's still that much easier to just rebuild the container targeting your CPU. It's so much easier to do to rebuild a container than it is to build software outside of a container, frankly. So I do have access to the chat, but I'm not up on the history. So let's see.
I don't really think there's any other questions. Just looking at the last one that I replied to and where we're at now.
Cool. Yeah. All right. Well,
If they did what they said they were going to do, it apparently Slurm with PMix was fixed in the latest version, and it got past me. I didn't notice it had come out.
Okay. Yeah, I think the one that I have installed right now still does not have it, but I haven't like switched. I haven't updated it, like I said, in a while. When putting a demo like this together, we try to leave it static so that it remains consistent. But yeah, that's great.
Cool.
All right. Well, I guess I can click this stop button and hand it back over to Dave, who's going to show us some really cool workloads, and I think some of them running in Fuzzball. So that'll be exciting.
Yes, I hope almost all of them running in Fuzzball. So if you're anything like me, that just blew your mind. When Jonathan showed me his when he showed me this this demo that he did before actually doing it live here, I mean, to have fully containerized MPI and run it on the system without having MPI in the system, I thought was pretty amazing. I'm going to start off my portion, my second portion of the demo here by doing something a little bit fun. So hopefully kind of wake everybody up and get everybody engaged a little bit. This is kind of a race. So I've put in the chat. Yeah, okay, here we go. So I've put in the chat, if you guys could give me some suggestions for so this is an HPC+AI conference after all, right? So if you guys could give me some suggestions for some interesting images that you would like to see AI generate, I'd like to put in a request to make some, to create some AI images through Fuzzball really quick, and then we'll return to those at the end of the discussion here. So far I have a fuzzy ball. Does anybody want to add any extra to that? So dancing dog. How about maybe a dancing fuzzy ball with a top hat, and then we can add more onto that if anybody's got any more ideas. So just keep them coming. And I'll tell you when I think we've got enough. And I should say that this is Dave's ceiling fan. Yeah. A dancing fuzzy ceiling fan with a top hat, or maybe a dancing fuzzy ball with a top hat in front of a ceiling fan. Yep. And then I think Jonathan is with a green balloon. With a green balloon. I'm going to leave the Dave's face. Okay, so this is good enough. I'm going to leave the Dave's face part out of that. I don't really want that anything to do with my face on AI. All right. So I'm going to go ahead off screen here and submit that to Fuzzball. This is going to be a little bit of a mystery for you guys to kind of work out what I'm doing here off screen, but by the time that we're done here, this is all going to make sense, hopefully. Okay. All right, cool. Yeah, okay. So we're going to go ahead and share the screen again. I'm going to share my second screen. You guys can see this. Okay, and so these are like some commands that I just ran to, start this workflow running. We're going to return to this workflow at the end. So one of the things that I kind of wanted to show you, so this third part of the talk, broadly speaking, is about HPC everywhere. So now we're going to step out of talking about HPC, using your on-prem hardware. We're going to start talking about HPC using, the cloud providers, like, choose your cloud provider, or maybe HPC on, a powerful workstation that you've got in your office or something like that. One of the things that I did not demonstrate earlier that I kind of wanted to talk about now is that Apptainer has the capability to really easily leverage GPUs, to really easily leverage the host system network. And I wanted to show all that to you within the context of a node on a cloud provider. So I'm going to show you, I'm going to SSH really quickly here to a single node that I've spun up on a cloud provider called Vultr that we use pretty extensively for testing here within CIQ. And I want to show you a few things about this. Number one, this has got a GPU inside of it. So I've got access to a GPU by spinning up this instance. And then I've got this directory here called TF example or TensorFlow example. So what I wanted to show you, this TensorFlow example, I'm going to actually CD into the directory. This TensorFlow example, this I have an image here, a CIF image, a container. And this is just a container that I've pulled directly from the NVIDIA container registry, NGC. So this is a default TensorFlow image that I've grabbed. And then I have this IPython notebook. We were talking a little bit about Jupyter earlier, so I want to kind of demo, if you were a user who wanted to do some development and wanted to use Jupyter from within a container, this is a really easy way to do it. And moreover, I'm running up on a cloud service here on a remote node. So I'm going to go ahead and execute this Apptainer command. So I've got Apptainer already installed on this node. And I'm going to pass, so I'm going to say basically execute Jupyter Notebook inside of this TensorFlow image. And I'm going to pass this --NV option. And at a very high level, what you can think of that as doing is passing the GPU, which is on the host system, through into the container. Okay. And so that's going to go ahead and spin up a notebook for me. Because I'm on a cloud instance here, I also have to set up a tunnel. So I can do that with SSH with this -L option. I don't know if hopefully everybody can see that. And then while I'm logging into this, I'm going to go ahead and just run a watch command for to just watch the GPU while I'm running this. Okay, so now I need to connect to this this instance. And I'm going to change that host name to local host. And I'll drag this over. This is off screen. You guys can't see this. And you can see this is a local browser that I've got running on my local machine. And just with a very few commands and with an off-the-shelf container that I grabbed from NGC, I'm now looking at a Jupyter Notebook here. And I can open that up and I can open, I can see this Jupyter Notebook. And I'm going to run this really, really simple example here, which is based on the MNIST data set. So if you've been around the deep learning AI community for a while, the MNIST data set is really well known. It's the modified National Institutes of Health or National Institutes of Science and Technology handwritten digits data set. And this is used a lot of times for examples such as this, or like, for just building small models. So I'm going to go ahead and run it. And basically what we're going to do here is we're going to download the MNIST data set. We're going to create a very simple model, and then we're going to train that model on the data set so that we can recognize handwritten digits. And we're going to do that in 10 different epochs. You can see over here that I've got some GPU utilization happening. We've got this Python process running on the GPU, and the accuracy is improving. We're going to get up to close to 98, 99% accuracy just with this really quick, simple little model. So there we go. We're around 98% accuracy in recognizing handwritten digits with this really, really quick little MNIST example. And so I just wanted to show that to you to just that was something that I left kind of unfinished, I believe, is that I didn't really show you how Apptainer is able to utilize GPUs, and also I didn't have to set up any network anything in order to do this. Apptainer by default uses the host network, and so the only thing I had to do was just use another shell here to set up a SSH tunnel to access this network. Okay, so but when we're talking about HPC in the cloud, this is kind of a corner case, right? This is not really HPC. This is just like, scientific user using Jupyter Notebook to do some development. Normally, you're not SSHing directly into a single node and using that within, the context of high performance computing. So now I want to shift gears and start talking a little bit more about actual HPC everywhere, like I said earlier. Let me go back to my slides here. Okay. All right, so now, so it's been kind of hard, if you've been in HPC for a while, there there have been pushes to try to get, I'm sorry, you can hear my daughter upstairs for a little bit here. There have been pushes to try to get high performance computing to move to the cloud for some time right now. And I think that's been hard because there's this disconnect between the HPC community and the cloud native communities. And I think that some of that disconnect is just sort of cultural, and people use different words to describe the same things and so on. But some of that disconnect is really about the underlying technology and the underlying goals of these two different communities. And I think at a really basic level, one of the biggest things that we can highlight is that a typical cloud native user versus a typical HPC user are interested in running different types of jobs. So in the cloud native world, when you're talking about running some kind of a workflow or something, you're almost always talking about running, like 95% of the time, you're talking about running a service. That is a process which starts, but is not expected ever to end. And which sort of sits around, forever and listens for requests and then maybe serves something up and does something, but just runs in perpetuity. And so because of that, when you need to do things like orchestration, for instance, you expect, certain things. You expect that your orchestration tool is going to, it's going to make sure that if your VM or your container, which is running your process, dies, that it starts back up, it fails over. You're going to expect things like, load balancing and, scaling up of your services if you have high demand and, stuff like that. And these are problems that you're going to have, which are very important to you, and which are so important, in fact, that they're baked in at the very lowest levels of cloud native kinds of orchestration tools. And that's great. The problem is if you're an HPC user, you're running fundamentally different types of jobs. You're running jobs that have a start and an end and are expected to produce a result. And maybe you've got multiple jobs which are dependent upon one another in order to run. They're not necessarily all expected to run at the same time. Maybe some of them run in parallel. Maybe some are dependent on each other. It's kind of fundamentally different from what the cloud native community is looking for and is trying to do with orchestration. And so if you take something off the shelf and try to do it for orchestration within HPC that already exists, you're going to find, number one, that you're going to have to learn a lot about problems that other people have that you don't have, that you're still going to have to know about and know how to deal with in order to use these tools. And furthermore, the problems that you're trying to solve, you're going to have to sort of hack together stuff to make it work, because that's not really what it was intended for. If we go all the way back to the origin of Apptainer, this was kind of the problem that we had 6 or 7 years ago when people started to ask about Docker being installed in the HPC system. It wasn't a good fit. And so I would postulate that we are currently at that same inflection point, the same kind of place that we were previously with orchestration tools. We need to find an orchestration tool which is going to fit the needs of our users. So what do? Well, I say that it's time for us, and actually others say and have said and have done, it's time for us to go back and ask, what do our HPC users need out of an orchestration tool? Just the same that Greg asked 6 or 7 years ago when first creating Singularity, what do the HPC users need? Well, users need to orchestrate their jobs. But once again, this means something a little bit different than what it means to your typical cloud native user, right? Orchestration in this case means jobs that start and end and depend upon one another. Maybe some of them can run in parallel. Maybe the workflow fans out and runs lots of jobs in parallel and then fans back in and runs 1 or 2 jobs in serially. But that's what we mean when we're talking about orchestration in an HPC environment. We need to be able to specify these workflows in a generic and portable way with some degree of hardware abstraction. And so we need to be able to create some sort of a specification which we can take and we can run on-prem, or we can take to one of the cloud providers and we can submit there and we can run there, or we can run locally, just whatever. This is a hard one. We need to be able to utilize diverse storage solutions like on-prem storage, maybe S3 cloud, storage, buckets that you've got in different places, or maybe just things that are kind of laying around the internet in different places. We need to be able to pull them together and, take that and pull it together with our compute and make everything, co-locate everything in the same place virtually, in our job. And then finally, if we're talking about, S3 buckets, or if we're talking about getting containers from private registries when we run our jobs, or, there's many different instances in which we need secrets or personal access tokens or passwords or whatever, and we need to be able to manage those secrets both easily and securely. And so these are all the exact kinds of problems that Fuzzball is designed and overcomes and instantiates. So Fuzzball is basically orchestration, which is designed by HPC people for HPC people. All right, and that is the extent of my slides. So once again, I just want to dive in here and do more demo than I do slides. Okay, so I've got a bunch of different examples here, and I want to start showing you these examples. What is Fuzzball? Before I jump into all these, maybe I need to talk a little bit more about just what Fuzzball is. So for these examples, we have a Fuzzball instance, which is running on AWS. And I've authenticated to this instance using single sign-on. Fuzzball is going to be able to be set up so that you can authenticate using, whatever type of authentication you've got currently within your, within your environment that you allow your users to authenticate with. But so I've got this Fuzzball instance running up in AWS. And what this is a cloud native kind of microservice architecture where these Fuzzball services are sitting there running, and they're waiting for me and for other users to submit job specifications or workflow specifications. And these workflow specifications, we specify these in YAML files. And so there's this, Fuzzball service that's up there just waiting for me to submit jobs to it. And when I submit jobs to it, what's it going to do? Well, it's going to, my jobs need to have containers to run in. So it's going to go find those containers, and it's going to pull those. It's going to figure out what kinds of resources I need to run the jobs, and it's going to allocate those resources as far as the actual compute that I need. Then it's going to go find containers, and it's going to, pull those containers to those resources. It's going to take any volumes of any like S3 buckets or any storage anywhere that I've got that I can specify, and it's going to go ahead and mount that storage to those jobs. And then it's going to execute the commands that I tell it and save the data wherever I tell it to save the data. So that's what's going to happen when I submit a Fuzzball job. All right, so let's actually start looking at some of this stuff and get a better sense of what it actually looks like. I'm going to go ahead, I'm going to start submitting jobs to Fuzzball. And then after I submit the jobs, I'll go through and I'll talk about what I actually just did, because that way the jobs can run while I talk. Okay, so my first job is this very, very simple YAML file that I'll go through in a second called printer.yaml. When I submit that to Fuzzball, it's going to tell me that I have a workflow started. I told it that I wanted to watch the workflows. That's why it's giving me this output. It's got a workflow that started here with a unique identifier. Within that workflow, there's an image that I need, and in this case, it's just an Alpine image. There's a job that needs to run. In this case, it's just a single job, and it's called printer. And it's going to tell me when these things start and when they end. So let's go ahead and look at that YAML file that I submitted. Okay, so the YAML file, I'm going to go through this line by line. This is how you specify a workflow within Fuzzball. So in this case, I'm telling Fuzzball that I'm going to be using version 1 of the spec. I've got this jobs section, which in this case only has one single job, and that job is called printer. I've named that printer. That job requires an image to run, and the image can be obtained from this URI, basically just from Docker Hub, and I'm going to be running the latest Alpine image. Once I get that image, I'm going to execute a command inside this job, and this could be just a series of commands like it is here, or it could be that you've created a script that you're going to run, and you're going to just execute that script or whatever. In this case, I'm invoking the shell, and then I'm saying I'm running a loop, and I'm saying for II in the sequence of 1 to 300, I want to echo the current iteration that I'm on, and I want to echo that again and send that to standard error. So I'm going to echo it twice, one on standard out and once on standard error. I'm going to sleep for a second, and then I'm going to do it all over again. So basically count to 300 in 1 second intervals for 5 minutes, because that's, 300 seconds is 5 minutes. Here I've specified a policy, and I've said if this job doesn't run in 10 minutes, then time it out. That's my timeout policy, and that's sensible because this thing should run in 5 minutes. I've allocated some resources here. So a single core with Affinity NUMA. This actually doesn't really make much sense in the case of a single core, but this is here to show that you can specify at a really low level, like what kind of topology, or what at a very low hardware level, how you want these jobs to be allocated. And then I've got a single gigabyte of memory is how much, which is way more than enough to just print out a bunch of numbers. All right, so I'm going to go ahead and get some logs out of this job while it's running to show how it's running. So to do that, I'll do a fuzzball workflow log. I want to follow those logs to watch them in real time. And I want the logs from this workflow from the printer job. Oops, not from that. From the printer job, not the printer.yaml. Okay, and then we can see that this thing is counting in real time. So I'm getting 2 numbers counted out in real time, from this job. Okay, that's a really simple example. I'm not actually going to submit the next one in the interest of time, but I have another YAML file here called 2OS printer. And so if I show you this YAML file, you'll start to get an idea about how parallelization and also running jobs in serial is carried out. So if I look at this one, this job is pretty much exactly the same as the other job, but now, or this workflow, I'm sorry, I need to be more careful about my terminology. This workflow is just the same as the other workflow, except it's done twice, and it's done with 2 separate images. So the first job is called printer Alpine, and the second job is called printer Rocky. And now I'm pulling 2 different images. I'm pulling an Alpine image, and then I'm pulling a Rocky Linux image. And then I'm going to do the same thing. I'm just going to count from 0 to 300 in 1 second intervals in both of these jobs, and all the resources and everything are the same. The difference here, number 1, is the fact that I've got 2 different jobs with 2 different images, and number 2, I could put this requires keyword in here. And what this would say is that I want my printer Rocky job to start after the printer Alpine job is finished executing. So this is how you set up simple job dependencies with Fuzzball. Or I could just comment that out, in which case both of these jobs would run simultaneously. And that's how you set up and do, that's one way in which you set up and do simple parallelization within Fuzzball. Okay, so I'm going to go through a lot of toy examples here pretty rapidly to give you a sense of what Fuzzball can do and how it can do it. And then at the end, hopefully there'll be time, I'll go through a few more kind of in-depth examples. Okay, now, so I showed you how you can do parallelization across just 2 jobs running at the same time. But what if you have 1,000 jobs? What if you have a ton of jobs and you in an embarrassingly parallel high throughput computing kind of workflow that you want to run? Well, I've got this this YAML file here called lolcal.herd. I'm going to go ahead and submit it. Fuzzball workflow start. And then after I submit it and it starts running, I'll look at it and I'll kind of show you what it's going to do here. So if you've been around the Apptainer / Singularity communities for a while, you know that there's a pretty famous container called LOL-cow, which is, basically become the unofficial hello world of Apptainer. I almost always demo that in some capacity. So I'm going to demo that here. And in this case, I have a whole herd of cows. So this is how you do parallelization if you have like an embarrassingly parallel workload within Fuzzball. In this case, I'm going to be pulling this LOL-cow image directly from Docker Hub, and then I'm going to echo I am cow number, and then this is the important part, this Fuzzball task ID or FB task ID environment variable. And so this is how you know what the task ID is from within a Fuzzball job. And then I'm going to pipe that to cowsay because it'll give it some ASCII art flair. And this is the other important part. So I've got this task array section that I can add to my job, and I can tell it where I want to start, where I want to end, and how much concurrency I want. So in this case, all 5 of these jobs are going to run at the same time. So let me use Fuzzball workflow status to get an idea of where this job is and whether or not it's completed. Looks like it did complete. And so now I'm going to do Fuzzball workflow log, the name of the workflow, the name of the job, and then I'm going to give it task ID. Let's do 2 just for fun. And now I'm going to get the logs from my second task, which was cow number 2. I can do the same for cow number 3, cow number 5, and so on. And so that's how you do, and this is kind of a simple little trivial example, but I hope that you can appreciate how, you could use this Fuzzball task ID. For instance, you could submit a file that has a single command on every line, for instance, and you could use this task ID to say, okay, I want you to execute, whatever's on line 900, because that's the task ID that you are. And then you could use this to build up, if you have like 1,000 files that you need to analyze in parallel, you could build this up and run, 1 to 1,000 and concurrency of, 1,000 if you want them all to run at the same time, or 100 if you want to run, 10 serially or whatever. So this is really, it's simple and it's powerful. It lets you do a lot of different things. Okay, so that's like high throughput computing, embarrassingly parallel stuff. What about actually high performance computing, MPI? Okay, so I'm going to go ahead and run the exact same example that Jonathan ran earlier in his demonstration on MPI within containers. So I've got this MPI hello world.yaml file here, and I'm going to introduce something a little bit different with this file in particular. Let's see. So here, this is a container that Jonathan built, and he built it within Apptainer, and he pushed the CIF file to a Google container registry that's a private registry that only we have access to. So I have here, I'll go ahead and show you this. So I am going to create a personal access token using this gcloud auth print access token command. And then I'm going to pass that personal access token to my Fuzzball workflow like so. Okay, that's going to go ahead and start, and then I'll show you what that does here in a second. So if we look at this MPI hello world, okay, once again, we have one job here. It's this MPI hello world job, and it's going to utilize a container from a private Google registry that I'm going to get using the ORAS protocol. So this is a container which was saved as a CIF file, and I'm going to pull it down as a CIF file, and I'm not going to use like OCI to stitch it back together or whatever. Because it's private, I need to pass some secrets. The username is just going to be this OAuth2 access token, because I'm going to use a personal access token through OAuth, which is going to expire in like an hour. And it's that personal access token that I just created. So this is a templating mechanism where I can then pass either through a file or through an environment variable, and I can pass that access token in. This is what we call client-side templating. I'm not going to demonstrate it today, but it's worth noting that you can actually do something which is a lot better and a lot more secure with Fuzzball. You can actually push your secrets to a Fuzzball, to a secret server that we have up in Fuzzball. And then you can use what we call server-side templating to, with a little bit of a different syntax, to grab that secret out of the secret store at runtime and plug it into your job and then be able to use those secrets at runtime. And so then this is the other kind of interesting thing to look at here. So I'm using this multi-node directive. And the multi-node directive is going to say that I want to run on, multiple nodes. I'm going to specify 2 here. And I'm going to specify that the implementation is OpenMPI. Okay, and as Jonathan said earlier, recall that I'm running here in AWS. AWS has EFA, which is the Elastic Fabric Adapter, which is like AWS's version of a high-speed interconnect. This particular container that I'm using doesn't have EFA support, so this is just going to run over Ethernet. But we just tried like 5 minutes before actually the demo started to put EFA support in there. We didn't quite get there, but I'm sure that this would run really nicely and really easily with the EFA support if we put that in there. So let me go ahead and really quickly Fuzzball workflow log. Get the logs out of this workflow, and the job is, I believe, MPI hello world with underscores. Okay. And so we can see that this did the right thing. It ran across 2 different nodes, as we can see by these IP addresses here. And I've got rank 0 and rank 1. And once again, this is even easier with Fuzzball, actually, like for Fuzzball to implement on the back end than it is on like a traditional HPC system, because everything is containers in Fuzzball. So you don't have that containery boundary problem that Jonathan was talking about earlier. Okay, so this has been a very, very quick whirlwind tour, and I've just showed you basically a bunch of just toy examples. I'm going to, in the last few minutes, try to show you just 2 more complicated examples. So the first of these is BLAST. BLAST stands for Basic Local Alignment Search Tool. This is a tool that's widely used within the genomics community, and it's something which is created by NCBI and at the NIH. And I'm going to try to go ahead and run this. In the interest of time, I'm just going to copy and paste a command to run this. So in this case, I'm just going to be using a container that already exists up on Docker Hub, which is published by NCBI. But I'm going to be mapping an S3 bucket to this container so that I can actually capture the output. So far, the only thing that I've showed you is just grabbing stuff out of logs, and that's fine. But you might actually want to analyze some data and actually save the your analysis. And so to do that, you need a place to save it where you can actually get it later. So this is going to demonstrate how you can do that. Okay, this is a bit of a more complicated YAML because there's number one, we're defining some volumes that we can copy our data out to an S3 bucket where I can get it later. And then number 2, this is more of a pipeline. There are several different jobs here which all kind of run in sequence. A few of them run in parallel, but some of them run in sequence in order to do this analysis. So I'm going to show you here, I'm creating a volume that I'm just calling V1. It's ephemeral and I'm using it for egress. And so what I'm going to do here is when this job finishes, it's going to save at the root of V1, something called results blastp.out. And I'm going to copy that over to an S3 bucket that I've got here. And I'm going to change its name to blastp valid results.out. And so I'm going to have access to that, when this job ends. And then of note here, I don't have time to go through it in detail, but I'm mounting this volume to the location / data within the container within all these jobs. And then these jobs are set up with dependencies upon one another. So this first one just creates a bunch of directories, and it doesn't have any dependencies. Obviously, it's just the first job. But then the second job needs the create directories job to run. It's going to download some data into one of those directories I just created. The third job also uses create directories to download data, or actually depends upon create directories to download data, and it can run in parallel with this job. So the two of these have the same dependency and they can run together. The next job is going to create some databases, and it has a dependency on both of the previous jobs to run. So this is an example of the jobs that I was talking about that might fan out. In this case, we just fan out into two parallel jobs, and then we fan back in. So, but you can, basically the way in which the YAML files are created, you can, come up with any kind of directed acyclic graph or DAG that you want to run. You can do so within Fuzzball. All right, I'm going to get the status of this job. I hope that it's already done so I can show you that I've got, cool, and it's done. So I can show you now that I've got this, result saved within AWS. I'm going to go ahead and authenticate. That allows me to authenticate, so then I can query this AWS bucket. And so recall that I saved in my S3 bucket this blastp valid results.out. I'm going to use this AWS S3 ls command to just check it, and I can see, cool. For my time, it's 2:27, so this was made 5 minutes ago. All right, so let's check back in. This is really, really quick, really whirlwind, and I just want to return at the very beginning of when I started talking here. I started talking about, I asked for some input on some crazy picture that we should make, right? And so I'm actually using stable diffusion. And so I have not created. Forrest Burt, one of the other really super smart solutions architects at CIQ, created this stable diffusion demo that basically uses Fuzzball to create a stable diffusion instance, and then asks that stable diffusion instance to create, based on something that you give it, some text that you give it, an image. And in this case, we decided to look for a dancing fuzzy ball with a top hat in front of a ceiling fan with a green balloon. So let's see how our custom stable diffusion instance did with that. So the first thing I'm going to do is just make sure that it actually created. And one of the cool things about this stable diffusion demo, so it uses, not only does it use egress. All right, so this this finished 2:04, so yeah, a little while ago. So not only does this this egress a final result, egress some data, but it also ingresses data from the S3 bucket using the YAML file. So Forrest was able to save some data, which is important for this model to run. And we're able to link that S3 bucket up with this job on the fly, and then ingress that data and use that. And it also uses GPUs. It uses V100 GPUs. And I can show you that syntax here if there's time for me to show it to you. It's really, really simple. I'm just going to untar this really quick. And the place where this is, so this is a lot of different images. The place where this is saved is that data, text to image. This is all 6 of the images that it created all in one big montage. Okay, and here we go. A fuzzy, what was it? A fuzzy ball with a top hat and a green balloon. I don't see any ceiling fans.
The ceiling fan got lost.
Well, stable diffusion has to make some artistic decisions as it decides what to present here. All right, so hopefully that was a little fun thing to keep you awake towards the end. I can really quickly show the stable diffusion.yaml. Here's how we are specifying the GPU devices here. It's really, really simple because of the fact that, because of what we have, what kinds of instances we have configured with Fuzzball. That's why we see this. This is the way that this works, and it gets us a V100 image. And then I'm sorry, I know I'm over time, and I'm really sorry about that. One quick thing before I go. I was asked by our CEO, so I better do it, to show. I showed everything at the command line today, right? Which is awesome for this group because this is a very technical group that really enjoys the command line. But if you have users that want to use Fuzzball, guess what? We're developing a really nice graphical user, web-based user interface. I'm just going to show you a few screenshots from it. I'm not going to go through it in detail. I'm just going to kind of give you an idea of what it looks like really quick. But Greg asked me to show this, and so he'd be mad if I didn't. I don't even know if I'm allowed to share this, but I'm showing it anyway. All right, so here's to give you a quick idea of what this looks like in the web. And that's all I've got. If there's time for questions, I'd be happy to answer them. I'm sorry I went just a little bit over time. Thanks very much.
Thank you. I think there was one question here. How can we do the accounting in Fuzzball?
Yeah, so I didn't go through it at all, but there's this entire kind of account hierarchy which exists here. So let's see. So within Fuzzball, you are part of, so first off, you can have multiple different Fuzzball clusters, which we call contexts, which you can kind of swap between and you can submit jobs to. Within each context, you are granted a particular account. So you are either an owner of or a member within that account. And so then the way that is all set up, and the way that that facilitates the use of authentication, and also facilitates the use of tracking, so that we can then take within Fuzzball. And this is something that we're developing. It's a very important part of Fuzzball that we're going to put together. Because the way in which this account is set up, you can go back through and you can match and you can figure out specifically, cycles, or you can track this with dollars, or whatever you need for each particular user, and also each particular member of account within the organization. So that's definitely something. I didn't get a chance to show it at all in this really quick demo, but yeah, that's definitely something that's very important and a basic part of the Fuzzball architecture.
And that was the only question.
Will Fuzzball be available for on-prem use? Yes. So that's the idea behind Fuzzball, is that, once again, we're talking about HPC everywhere, right? So now, instead of I've got a Slurm submission script which runs on this cluster, but when I take it to this other cluster, it doesn't work anymore, or I can't even begin to take it up to the cloud because the cloud doesn't grok Slurm or whatever. Instead of that, now you've got this Fuzzball specification which runs on-prem, it runs on AWS, it runs in GCP, it runs when you submit it to your powerful workstation that you've got sitting under your desk and you got Fuzzball running on. It runs anywhere. That's the idea.
And just to be clear there, that the on-prem capability is already in place. Like, more of our POCs have been on-prem, I think, than in the cloud externally.
Yes, thank you. I talk about a lot of this as though it's the ideal, but it's not the ideal, it's the reality at this point.